Hi, this is Calculus 12, Chapter 6.5. We're going to be looking at population growth. We're going to compare the exponential model to another model and see how they perform. We have exponential growth, such as bacteria, and the model is sufficient for small populations and small intervals of time. If a simulation runs long enough, the numbers will blow up. For instance, if we use exponential growth for humans, it won't take long before the number exceeds 30 billion. We know that there aren't enough resources for the population to keep growing. A more accurate model is the logistic growth model, which takes into account of limited resources. And this is called the logistic function. And we hear of examples where exponential growth doesn't apply. We hear of cities that are getting overcrowded and they can't support more people. You could build more buildings, but is there the infrastructure to keep that population growing? Are there enough roads? Are there enough schools? Is there enough water? So all these are logistical things, and that's why we call this the logistic function. So we have a new differential equation. The dp dt equals k, some constant factor, p over m times m minus p. So this is very complicated to look at. It becomes a little bit easier if we remind ourselves what's going on. This is the change of population over time, dp dt. And it keeps growing up to the carrying capacity. So this is the ideal population size. If our population is below this ideal size, this is positive. So we have positive population change. However, if our population is bigger than our ideal size, then this becomes negative. So we lose population. And that's one of the rationales for using the logistic function. So M is called the carrying capacity. How big is the population that the resources will permit to grow? K must be greater than 0. So we need to solve this differential equation. That means we need an explicit function for P. So we do what we normally do. We separate and integrate. This is a constant. This is a constant. And let's move all the p's over to one side, and we'll leave t on the other side. So this and this and this all go over on this side, and dt goes over on this side. We'll leave k on the right-hand side. Okay, so separating, we get m dp over p, m minus p equals k dt. And we need a little trick to integrate this because that's difficult. We need to split this up into fractions. And we use a trick, 1 over p plus 1 over m minus p equals. We need a common denominator here and here. So this gets multiplied by m minus p over m minus p. This gets p over p. So we get m minus p plus p over p, m minus p. These two cancel out. We get m over p times m minus p, which is what we have here, m over p times m minus p. So let's write that out, 1 over p plus 1 over m minus p dp equals k dt. We integrate both sides, and we want to split up this integral, 1 over p dp plus integral 1 over m minus p dp equals integral k dt. Okay, now we have ln, and this is just a constant. So we have ln absolute value of p plus ln absolute value of m minus p, equals kt plus constant. Sorry, this is a minus. This minus means we divide our two parameters. So we have ln absolute value of p divided by m minus p equals kt plus c. Nothing changes on the right-hand side. And a little trick here to help us move this into the numerator is we want to do this to the power of -1. That means we negate this other side. So ln m minus p over p equals minus kt plus c. So we could do a minus c, a plus c, it doesn't really matter. It's going to be a constant in the end. Now we exponentiate both sides with base e because this is a natural logarithm. So m minus p over p equals e to the negative kt plus c. Now we want to split this apart. M over p minus 1. And we'll take e to the c as just a constant. E to the minus kt, m over p equals 1 plus a e to the negative kt. Let's bring this up here for our general solution. P of t, we're going to reciprocate this. That means this is going to the denominator. And then m comes to the top. And we have 1 plus a e to the negative kt. This is our general solution. Again, some profs may want you to derive this on a test. I will not be asking you to derive this on the test. You can go ahead and just use this formula. Working with this equation, we want to solve for a. So a equals m over pi minus 1 times e to the kt. Okay, since we're dividing this side, we can move it into the numerator and change that to a positive. And that's why we have positive over here. Now this simplifies to m over p naught minus 1 if t naught equals 0, or if you like, if t equals 0. Then we can use p naught. Okay, again, very confusing until you go through a solution. So let's look at an example. Biologists are stocking a lake with 400 fish and estimate the carrying capacity to be about 10,000. The number of fish triple after the first year. Use the logistic equation to determine when there will be 8,000 fish. And let's compare this with exponential growth. Let's pick off values. This is our p of t that we're trying to solve for. This is 3. This is p naught. This is our carrying capacity. And we can use the formula we just derived. So we start off with a, because we know m, we know our time to be at t equals 0, and we have p naught. It's always best to rewrite the formula until you've memorized it, m over p naught minus 1. So this is 10,000 over 400 minus 1. And that's 24. We still need to figure out k. So we're given an initial condition, and this is at t equals 1, because it's after the first year. So let's write our equation out first. P of t equals 10,000 over 1 plus 24 e to the minus kt. Let's substitute P of 1 equals 3 times 400 equals 10,000 over 1 plus 24 e to the minus k, because it's after 1 year. So 1,200 equals 10,000 over 1 plus 24 e to the minus k. Because this is in the denominator, I'm going to move this over to this side. We have 1 plus 24 e to the minus k equals 10,000 over 1,200. Let's cancel some zeros out. Let's move the 1 over to the other side. So 24 e to the minus k equals, let's simplify this a bit more. We can divide it by 4. We get 25 over 3 and minus 1. Divide both sides by 24, e to the minus k equals 22 over 3, and then we have another 24 in the denominator. Take the ln of both sides, minus k equals ln, and we can simplify this to 11 over 12, so we have 11 over 36. And we can flip this over because of the negative sign. K equals ln 36 over 11. So let's plug that in again. P of t equals 8,000 equals 10,000 over 1 plus 24 e to the negative kt. Again, I don't want to substitute this in because I don't want to keep on writing this out. So I'm going to move this over to this side, move this over to this side. 1 plus 24 e to the minus kt. And this reduces to 5 over 4. 24 e to the minus kt equals 5 over 4 minus 1 is a quarter. Now we're going to divide by 24 as well. E to the minus kt equals 1 over 96 minus kt equals ln of 1 over 96. T equals, again, I'm going to take that negative sign and flip this over, so it's ln 96. Now we're dividing by k. I'm going to substitute this in, ln 36 over 11. And now we can plug it into the calculator. We have no rounding errors. We keep all our values until we actually need to calculate it. And if you plug this in on your calculator, we get 4.3 years. Now, I'm not going to do exponential growth. You did this in the previous section. So I'm just going to go through the numbers. So our initial stock is 400. We go ahead, plug in 1, and we solve for k, and k is ln 3. A of t now equals 400. E to t ln 3. We solve, do some algebra, and we solve. We get ln 20 over ln 3. This is 2.7 years. And you can see that the growth is much faster than the 4.3 years. And it's good to graph this. Be careful with the brackets on a calculator. and whether multiply signs are necessary. Okay, I'm going to bring out the TI. Okay, we have 10,000 divided by brackets. Remember, there's multiple terms, so we need brackets. 1 plus 24, and E is down here, so second. E negative ln 36 divided by 11 times x. And we have 1, 2, 3 left brackets. We have 1 right bracket, so we need 2 more right brackets. This is our logistic equation. Our exponential equation is 400 e to the power of x ln 3. And we have 2 left brackets, so we need another right bracket. We also need 8,000, which is what we're trying to solve for. Our window, we don't need negative numbers, but it's just interesting to see what the graph's going to look like out there. And let's make our y max 10,000, otherwise we won't see our solution. And graph. Okay, you can see this logistic function has slowed down compared to the exponential function. It behaves like the exponential function initially, but you can see that we're starting to get close to the carrying capacity here, so it needs to start slowing down in an exponential manner. And let's just take some screenshots of that. Paste it here. Logistic. Exponential. And the window. And our graph. And logistic at carrying capacity. And our exponential growth. Okay, so if you don't have this shape, you don't have a logistic function. So it's always good to be able to understand what kind of shape you need so that you can check to see if you've entered things properly on your calculator. Let's take a quick look on the Casio. Okay, let's enter this in. We have 10,000 divided by bracket 1 plus 24 e to the power of negative, and we need a bracket for this, ln 36 divided by 11 bracket x, and we need 2 more brackets, and we have 400 e to the power of bracket x ln 3 bracket. We have 8,000, and I've set my window here, and I need brackets around the ln 36. Okay, now that looks like our logistic function. And we have our exponential function. I'm not going to take screenshots of this because it's going to be similar to that. We just have extra brackets on the Casio that requires us to do that. Okay, another problem that you'll encounter. We have to determine M and K, and we have to use this form in order to be able to solve for it. So we need to use algebra to rearrange this. Typically, we're given a differential equation like this. You can be given a differential equation in any form. This doesn't quite look like this, so we need to do factoring. First of all, we need to remove the 50. First of all, we have dBdt over p. That leaves us with 1 over 50. And just leave this in its original form. We need 1 minus p. So we need to factor out a 2. That means we divide by 2. 2 over 50. 2 divided by 2 is 1. And 1 over 250 divided by 2 gives us p over 500. Simplify this, we have 1 over 25. 1 minus p over 500. Therefore, k equals 1 over 25, which is 0.04. M equals 500. And that follows this form, and we're allowed to pull out these values. And that completes this lesson.